This is Dr.S.Prasanna, Assistant Professor of Mathematics in Pingal Government College for Women, Warangal. I am dealing with the topic Linear Algebra for BSc Final Year Mathematics. So far, we have seen what is a linear combination, what is a span, and now it is null space and column space. These are also subspaces of a vector space, and this topic also includes linear transformations, wherein we can have two more subspaces. They are range, kernel, and range of the linear transformation. So in this topic we study more about subspaces of a vector space, and among them null space, column space of a matrix, kernel, and range of a linear transformation are the important topics we are going to study now. And all these are various types of subspaces of a vector space. In fact, kernel and range of a linear transformation are just the null space and column space of the corresponding matrix. So we in this chapter we are going to learn about four types of subspaces: null space, column space, kernel, and range of a linear transformation. All these are various types of subspaces, and if we broadly think of the kernel and range of a linear transformation, they are also can be treated as null space and column space of the corresponding matrix. So these are the various types of the subspaces we are going to study now. And in this video lesson, I want to cover about the null space of a matrix. Let us see what is the null space of a matrix. To orient into the concept of the null space of a matrix, let us first consider a linear system of homogeneous equations. And I want to take, even though I have three variables, I have chosen three variables x1, x2, x3. Now I am taking only two equations. These are the two equations I have taken: 2x1 minus 5x2 plus x3 is equal to 0, minus 3x1 plus x2 plus 4x3 is equal to 0. Now this system of linear equations can be written simply in a matrix form as matrix equation as Ax bar is equal to 0 bar, where A is equal to, as I have taken only two equations in the linear system, I should have only a 2 by 3 matrix. As there are three variables, there will definitely be three columns, but as I have taken two equations, there will be only two rows in the matrix A, which constitutes the coefficient matrix of the given equations. So capital A is equal to 2 minus 5 1 minus 3 1 4, comma x bar is equal to, it is a column vector with the variables are scalars x1, x2, x3, and 0 bar is equal to a 2 by 1 column matrix with the column vector with the vectors 0 0 with elements 0 0. Here we can understand that all these matrices A, x bar and 0 bar are satisfying the above matrix equation Ax bar is equal to 0 bar. To satisfy that, A is of order 2 by 3, as there are two rows and three columns, its order is 2 by 3. Now to multiply it to or to commute it to x bar should have order 3 by something. Anyhow, it is a column vector of order 3 by 1. We can commute A and x bar, so that 2 by 3 and 3 by 1 matrices after multiplication give some 2 by 1 resultant matrix. As it is a 0 vector, 0 bar, its order is 2 by 1. So that is how A is of order 2 by 3, 3 x bar is of order 3 by 1 and 0 bar is of order 2 by 1. Now the set of all x bar that satisfy the system of equations in 1 is called the solution set of equation 1. So whatever be the values of x1, x2, x3 we are getting, that gives the set, that decides the set x bar, and that set of all x bar, all that different values for x bar gives that, take them in a set, and that set is nothing but the solution set for the system of equations that we have taken in equation 1. Also, the solution set is non-empty. As we can see, the 0 vector of order 3 by 1, which always satisfies Ax bar is equal to 0 bar. When we take 0 vector of order 3 by 1 in the place of x bar, we are definitely going to get the 0 vector of order 2 by 1 as resultant vector. So that is how x bar is equal to 0, 0, 0. A column vector of 3 zeros is always a solution for the above system of linear equations. Whatever be the system of linear equations, we are taking such a system of homogeneous equations, then obviously the 0 vector will be a solution for that system. So whatever be the set of solutions, 0 bar is going to be included in that. So that is why the solution set for a system of homogeneous equations is always non-empty. At least the 0 vector 0 bar is present there. So the set of x bar, now we can lead to the definition of null space, which is the concept that the explanation so far we have can give. That is, the set of x bar that satisfy Ax bar is equal to 0 bar is the null space of the matrix A. That means whatever be the solution sets that satisfy the matrix equation Ax bar is equal to 0 bar, all those solutions taken in a set are called is called the null space of the matrix A. So the set null space of a matrix A is nothing but the set of all solutions of the matrix A satisfying the matrix equation Ax bar is equal to 0 bar. So from above we have seen that x bar is equal to 0, 0, 0. The 0 vector is always a solution for Ax bar is equal to 0 bar. We can say that the null space of the matrix A, which consists of all the sets, it is the set of all solutions of the matrix equation Ax bar is equal to 0 bar, is always non-empty for a given system of linear homogeneous equations. So now we can go to define in a formal way the null space of a matrix. So what is the null space of a matrix? How is it defined? Let us see. If A is a m by n matrix, then the set of all solutions to the homogeneous equation Ax bar is equal to 0 bar is called the null space of A, and it is denoted as null A. So this is the definition of the null space of a matrix. What it says is, if A is a m by n matrix, if A is an m by n ordered matrix, then the set of all solutions to the homogeneous equation Ax bar is equal to 0 bar. This is the matrix equation we are taking, but it is a homogeneous system of homogeneous linear equations, and this is the solutions of this equation Ax bar is equal to 0 bar is called the null space of A, and it is denoted as null A. Null A is the null set of all solutions of the equation Ax bar is equal to 0 bar. and it is denoted as null A. Therefore, null A in a notational form is defined as null A is equal to set of x bar such that x bar is in Rn and A x bar is equal to 0 bar. So, null A is the set consisting of all the solutions of Ax bar is equal to 0 bar such that x bar is in Rn. X bar is any column vector from the set Rn. R, R2, R3, R4, R in general Rn. So, x bar is an element from among any of these sets. So, this is the final definition of null space of A matrix. So, null A simply can be taken as the set of x bar such that x bar is in Rn and it satisfies A x bar is equal to 0 bar. Now, let us move on to some illustrations which are dealt as problems here. So, first one is we can treat these problems in both ways. They are problems in one way, and they are, if you do solve that problem, you can understand it as an example of the null space of a matrix also. So that is how these are illustrations which are treated as problems now. So let us go through the first problem. If A is equal to 1 minus 3 minus 2 is the first row, minus 5, 9, 1 is the second row, and u bar is equal to 5, 3 minus 2 is a 3 by 1 column vector, then we are asked to find two points. The first one says that find or determine whether the above vector, column vector u bar, belongs to the null space A or not. And in the second part, it is asked to determine the null space of A. The set itself is asked to be found. So let us move on to the solution now. In the first part, to solve the first part, let us consider whatever is given in the problem. Whatever be provided in the problem, let us consider them first. We are given the matrix A and the column vector u bar, and A is given as 2 by 3 matrix with 1 minus 3 minus 2 as first row, minus 5, 9, 1 as second row, and u bar is a column vector with the elements 5, 3, minus 2. Now, by the definition of null A is equal to set of x bar such that Ax bar is equal to 0 bar. So, let us write for the given matrix A in this problem. Let us see what is null A. Null A is equal to set of x bar such that Ax bar is equal to 0 bar. Now, null A is equal to set of x bar such that Ax bar is equal to 0 bar. Now consider AU bar. Now why am I considering AU bar? Because I want to see that in this part of the problem, I want to see that whether this column vector which is given to us is a solution or whether it belongs to the set null A, whether it is a solution of the matrix equation Ax bar is equal to 0 bar. So, u bar belongs to null A, or u bar will be in null space of A if and only if it satisfies the matrix equation Ax bar is equal to 0 bar. So, that is why I want to say whether the product AU bar gives us the 0 vector 0 bar. So, let us find the value, the matrix that we get for AU bar. After computing, what do we get? Let us see. So, AU bar is equal to 1 minus 3 minus 2 minus 5 9 1 time into 5 3 minus 2. We can say these two matrices are can commute because the matrix A is of order 2 by 3, whereas the matrix U bar is of order 3 by 1. So, the resultant matrix we should get should be of order 2 by 1. So, let us, first of all, they commute and the resultant matrix will be of order 2 by 1. So to multiply these two matrices, we multiply the first row with the column in the second matrix, and write the sum of the scale multiples of them in the first as the first element in the resultant matrix. And that is how we are getting 1 into 5 minus 3 into 3 minus 2 into minus 2. That gives us 5 minus 9 plus 4 as the first element in the resultant matrix. And the next element in the resultant matrix can be found by multiplying the second row with the column in the second matrix. So minus 5 9 1 when multiplied to 5 3 minus 2 with the corresponding elements and adding them, we get minus 5 into 5 plus 9 into 3 plus 1 into minus 2, that gives you minus 25 plus 27 minus 2. After calculation, we can see that this is equal to 0 0, which is a 0 vector. So somehow AU bar, we could show that AU bar is the resultant vector of AU bar is 0 bar. That means AU bar is equal to 0 bar is satisfied. Ax bar is equal to 0 bar is satisfied by u bar. When we replace x bar by u bar, the equation Ax bar is equal to 0 bar is satisfied. That means u bar is satisfying the condition for the null space, null A. So that is how u bar is in null A. Thus, u bar belongs to the null space of A. So they are asked us to determine whether the given vector u bar is in null A or not. So our solution to this is that the u bar belongs to the null space of A. Now moving on to the second part of the problem, we are asked to find the total null space of A. The set we have to find. So we are asked to determine the null space of A. For that, consider the matrix A given to us first. Then let x bar is equal to x1, x2, x3 be the column vector of order 3 by 1, which constitutes the variables x1, x2, x3 in the system of equations which give the matrix A. So then the homogeneous system of equations given by will be two equations. So from A whatever be the elements in A, taking them as coefficients, then forming the homogeneous system of equations with the variables we have taken in x bar, which are x1, x2, x3, we get two equations, and they are x1 minus 3x2 minus 2x3 is equal to 0, minus 5x1 plus 9x2 plus x3 is equal to 0. Now let us solve them in a manner that we usually do, solving of two equations. And I have solved the first equations for first two. Eliminate x2. So I have taken equation 1 into 3, so that it becomes 3x1 minus 9x2 minus 6x3 is equal to 0, and the equation 2 have not changed anything, just written below that 1 into 3 equation, and we can see 9 minus 9x2 plus 9x2 cancels out, and we will be left with minus 2x1 minus 5x3 is equal to 0. From this we are not going to get either the value of x1 or the value of x3, but neither the value of x1 nor the value of x3 as a real number, but we can write as a relation between x1 and x3 like this. I have written it as minus 2x1 is equal to 5x3, then I can have x1 is equal to minus 5 by 2 times x3. Let us suppose that this is the value we got for x1. So x1 is equal to minus 5 by 2 x3. And now substitute whatever that value we got for x1 in one of the equations, either 1 or 2. So I have substituted in equation 1, that becomes now minus 5 by 2 in place of x1, write the value that we got above, that is minus 5 by 2 x3 for x1. So the equation 1 now becomes substituting like this, it becomes minus 5 by 2 x3 minus 3x2 minus 2x3 is equal to 0. And now we want the value of x2 in terms of x3 now. So put my x2 term on the left hand side and other two x3 terms, take them to the right hand side and then add them up. On the right hand side, 5 by 2 x3 plus 2 x3 gives you, when after taking LCM, it changes to 9 by 2 x3. So it is 5x3 plus 4x3 by 2, which gives us 9 by 2 x3. And on both sides I have cancelled out that 3 on both sides. Now at the end we could get the value of x2 in terms of x3 as x2 is equal to minus 3 by 2 x3. So we are as there are only two equations, we can form only relations between the values of x1, x2, x3. So that is how we got x1 as minus 5 by 2 x3 and x2 as minus 3 by 2 x3. Therefore, our solution set x bar can be taken now represented as, or now can be taken as x1, x2, x3 is equal to minus 5 by 2 x3 minus 3 by 2 x3 and x3. So x1 we have replaced by minus 5 by 2 x3, that we got whatever the value we got above. In the same way, x2 is replaced by minus 3 by 2 x3, and this is the matrix formed now. Now taking minus 1 by 2 x3 common from all these three elements in the matrix, we can write it as minus 1 by 2 x3 times 5, 3, and as there is no minus half in the last element of the matrix, we should write it as minus 2. So after taking minus half x3 as common, so now we got that minus 1 by 2 x3 times 5, 3 minus 2 is the column vector, multiply to it. So the minus half x3, when we view x3 as a real number, that minus half x3 is going to be another real number or scalar, so which will definitely be some scalar among the real numbers. So let us suppose that minus half x3 as a single variable term as k. So let k is equal to minus half x3, and this set x bar now looks as x bar is equal to k times 5, 3 minus 2, where we know that k is a real number, or where k belongs to R. Now thus any real multiple of 5, 3 minus 2 is a solution of Ax bar is equal to 0 bar. That means Ax bar is equal to 0 bar in this which is a system of linear homogeneous equations, has infinite number of solutions given by k times 5, 3 minus 2. K, where k is any real number. So taking k as different real numbers, we can get infinite number of solutions for Ax bar is equal to 0 bar as k times 5, 3 minus 2. So that is how we can write the null space of matrix A, making use of this solutions set. How? Let us see now. We have the definition of null A as null A is equal to set of x bar such that Ax bar is equal to 0 bar. Now in this problem we have seen that x bar is the set of consisting of set of all k times 5, 3 minus 2 such that k belongs to R. So that is how our null A to this in this problem is the set null A is equal to set of k times 5, 3 minus 2 column vector such that k belongs to capital R. K is a real number. So this is the null space of the given matrix A in this problem. Also, as u bar is equal to 5, 3 minus 2, it is given in the problem. In the first part of the problem we have seen that u bar is equal to 5, 3 minus 2 column vector, and this is also when k is equal to 1, this belongs to u bar belongs to null A. When we take the scalar multiple of I3 minus 2, which is k, as a real number 1, fixed number 1, then we can see that u bar belongs to null A. So null A is in the span of u bar. So all the multiples of scalar multiples of I3 minus 2 gives the set, forms the whole set null A, and the scalar multiples of u bar are nothing but the linear combinations of u bar. As u bar is a single vector, all the scalar multiples of it are treated as linear combinations, and that is how null A is equal to the set span u bar, where span u bar is the set of all linear combinations of the vector u bar, and that is nothing but the null set A, null space A from above statement, above definition. So that is how finally the null A we can regard it as the span of u bar. Okay, let us now move on to the next problem, that is if A is equal to 3 minus 5 minus 3, 6 minus 2 0, 8 minus 4 minus 8 4 1, then we are asked to find whether w bar is equal to the column 3 by 1 column vector 1 3 minus 4 belongs to null A or not. So this is the question asked for us, and this we can do by considering the depending on the concept of the null space. How we can do it? Let us see. Given capital A is equal to 3 minus 5 minus 3, 6 minus 2 0, minus 8 4 1, and w bar is given as the column 3 by 1 column vector 1 3 minus 4, and we have, as I said, this problem we can to solve this problem we can make use of the concept null A. So for that reason I am making the trying the definition of null A to give in the next step. So null A is equal to set of x bar such that A x bar is equal to 0 bar. So the null space of A, the matrix A has the null space as defined as set of x bar such that A x bar is equal to 0 bar. So now our aim is to prove that whether that w bar belongs to null A or not. So w bar belongs to null A if it satisfies the matrix equation Ax bar is equal to 0 bar. How can it satisfy the matrix equation Ax bar is equal to 0 bar? In place of x bar, if we replace it by w bar, even then if aw bar is equal to 0 bar, then we can say that w bar is in the set null A, or we can say that w bar belongs to the null space of A, that is null A. Now consider what is aw bar. Let us see whether aw bar is resulting to the 0 vector after commutation. So consider aw bar. A is the matrix given to us, and besides that consider the column vector w bar. Now use the matrix multiplication concept and multiply these two matrices. The first one is a 3 by 3 matrix and the second one is a 3 by 1 matrix, and as 3 by 3, the number of columns in 3 by 3 matrix, which is 3, is equal to the number of rows in the second matrix, which is 3 again. As they are two equal, we can say that we can commute these two matrices and get a resultant matrix of the order 3 by 1. So let us see how we can get that 3 by 1 matrix, 3 by 1 column vector after multiplying these two matrices. The first row should be multiplied to this column, and adding sum of those multiples gives the first element of the resultant matrix. So we can multiply the terms like this: 3 into the first row with the column in the second matrix, 3 into 1 minus 5 into 3 minus 3 into minus 4, which gives us 3 into 1 minus 5 into 3 minus 3 into minus 4. The calculation we can do later. Now moving on to the second row, it is 6 into 1 minus 2 into 3 plus 0 into minus 4. Again we have done the same thing, multiplying second row with the column. Now the last row can also be multiplied to the same column and can be written as minus 8 into 1 plus 4 into 3 plus 1 into minus 4. And we can see it is 3 minus 15 plus 12, and the second row is 6 minus 6 plus 0, then minus 8 plus 12 minus 4 is the are the values that are obtained by above calculating the above 3 rows. Now it even simplifies to minus 12 plus 12 0, and the third row element is also minus 12 plus 12. Then that gives us the 0 vector 0 0 0. So that is how AW bar is equal to 0 bar. So AW bar, as it is happening that AW bar is equal to 0 bar, W bar, we can say that W bar satisfies the equation AX bar is equal to 0 bar. That means W bar is an element of the null set null A. X, in place of X bar we can take W bar, and we have seen that AW bar is equal to 0 bar. So that is how we can claim that W bar belongs to null A. Thus W bar is equal to the column vector 1 3 minus 4 belongs to the null space of the given matrix A. So this is the solution for the problem 2. Now moving on to the third problem. If A is equal to a matrix given like this, it is also a 3 by 3 matrix with the elements 5 21 19 13 23 2 8 14 1. Even we are provided with the matrix like this A, we should think that this matrix A represents the system of linear equations in 3 variables. As there are 3 columns, we should suppose that there are 3 variables in the system of linear homogeneous equations, and we are given 3 equations which are simply written in the matrix briefly as capital A is equal to 5 21 19 13 23 2 8 14 1. And now we are asked to determine if W bar is equal to 5 minus 3 2. This column vector is in the null space of that above matrix A. So given we let us move on to the solution now, and we are given whatever be the given information, the take them first, consider it first, and A is equal to the matrix capital A is equal to given as 5 21 19 13 23 2 8 14 1, and W bar is equal to 5 minus 3 2. These are the 2 matrices given to us, and we are asked to find W bar, whether W bar is in the null space of A. So for that we need the definition of null A, and we know that null A is equal to set of X bar such that AX bar is equal to 0 bar. So null A is a set consisting of all those vectors X bar which satisfy the equation, matrix equation AX bar is equal to 0 bar. Now we want to see that W bar whether W bar belongs to null A or not. So W bar belongs to null A by the definition of above definition of null A, above definition set of null A, we can say that W bar belongs to null A if it satisfies the matrix equation AX bar is equal to 0 bar. That means if AW bar is equal to 0 bar, then we can say that W bar belongs to the set null A, or W bar is in the null space of the matrix A. So consider AW bar and let us see what whether it gives rise to the 0 matrix as the resultant matrix or not. Now taking AW bar, we can first of all verify whether these 2 matrices are commutable or not. compatible or not. So we can see that A is a 3 by 3 matrix and W bar is a 3 by 1 column vector, and the number of columns in A is equal to the number of rows in W bar, so that these two matrices can commute, and they give a resultant matrix which will have the order 3 by 1. Now moving on to the multiplication of these two matrices, we can do in the same manner that we have done in the earlier problem, multiplying the rows with the column and writing it the corresponding positions. We can have the first element as 5 into 5 plus 21 into minus 3 plus 19 into 2, and this is the first element. In the same way, the second element can be obtained by multiplying the second row with this column in the second matrix, and that is equal to 13 into 5 plus 23 into minus 3 plus 2 into 2, and in the last as the last element we can get it as when we can get it by multiplying the last row 8, 14, 1 to the column 5 minus 3, 2 with the corresponding elements, and we can see the last element of the resultant matrix is 8 into 5 plus 14 into minus 3 plus 1 into 2. Now let us move on to have the calculation of these values. The first row now becomes 25 minus 63 plus 38, and the second element is 65 minus 69 plus 4, and the third element is 40 minus 42 plus 2. So that is how it is equal to 63. 25 plus 38 gives you 63 minus 63, and next in the next second element 65 plus 4 gives you 69, and it is minus 69 there, and in the last row also we can see 40 plus 2 is 42 minus 42. In all these elements we got 63 minus 63, 69 minus 69, 42 minus 42, which definitely give the 0 matrix 0 0 0. So that is how 0 bar is the resultant matrix for the after computation of AW bar. We got the resultant matrix as the 0 vector 0 bar with which is a 3 by 1 column vector. So AW bar is equal to 0 bar, that implies W bar belongs to null A. That means W bar is in the null space of A, and W bar is equal to 5 minus 3 2 is in the null space of the matrix given matrix A. That is the conclusion. So with this my introduction in this video lesson, I have introduced the three terms: null, column, null space, column space, and linear transformations. And in linear transformations we are going to study kernel and kernel of a linear transformation and range of a linear transformation, and I am saying that all the four are subspaces and of a vector space. And so we are in this chapter we are going to study various types of subspaces of a vector space, and among the four I mentioned now, the last two, kernel and range of a linear transformation, are again nothing but the null space and column space of the corresponding matrix. So somehow the null space and column space are the basic subspaces of the of a vector space in this chapter. So to move on to learn them, I have start with I have taken the null space of a matrix for this video lesson, and we have seen what is the introduction to get the concept of null A, and we have defined the null space of a matrix, which is null A is equal to set of x bar such that A x bar is equal to 0 bar, and that is all the null A is the set of all those solutions which satisfy the matrix equation A x bar is equal to 0 bar, and we can see that x bar is some element of among any of the sets R, R2, R3, R so on, Rn. It can be a real number or a 2 by 1 column vector from with entries as real numbers, or a 3 by 1 column vector as entries as real numbers, or it is a Rn, n values in the column vector with who and which are all real values. So x bar is always with the real entries, and it is always a column vector. So that is about null space of a matrix, and then we have solved some problems based on that definition of null A, and in the later classes we will see some more problems. We will solve some more problems on this concept null A, and then there is a subspace spanned set of the null space, and that also we will see in the later classes. Okay, with this I will remind for today's video lesson. Thank you.